Good afternoon, everyone, and welcome to today's webinar titled Data Needs for Modeling. This webinar is sponsored by EPA's Water Quality Modeling Workgroup. My name is Jason Gilday with EPA, and I'll be moderating today's webinar. And thank you all for joining us today. Next, I'm just going to go over a few brief webinar logistics. We hope that you have a lot of questions during today's webinar. You won't be able to voice those questions, but you can type them into the box on your screen titled Presenters Questions, and then click Send Question. There will be several question and answer sessions throughout the day today where we'll be addressing the questions that you type in. If you have any problems viewing the broadcast, just let us know in the Adobe Connect Help box, and we will post an answer in that same box. This webinar will be archived for later viewing on EPA's Water Quality Modeling training page, and we provide that archive link for you at the bottom right-hand corner of your screen. Also, at the end of today's webinar, you will be able to obtain a certificate of attendance for participating, and we'll provide directions for downloading it at that time. The materials in this webinar have been reviewed by EPA staff for technical accuracy. However, the views of the speakers are their own and do not necessarily reflect those of EPA. Mention of commercial enterprises, products, or publications does not mean that EPA endorses them. So next, the purpose of this webinar is to help water quality professionals better understand water quality modeling and how models can be used to solve problems facing water quality regulators. The target audience for this series is a water quality professional who may use, want to use, or review models as part of their job, but who do not necessarily have a modeling background. As such, we are assuming that the audience has a basic understanding of water quality science and concepts, but has limited direct modeling experience. Today's webinar is actually the 20th in our water quality modeling series. All of the past webinars have been recorded, archived, and posted to EPA's YouTube channel. Links to the archived files are available on our Modeling Workgroup website. Again, this URL is shown at the bottom right of your screen. Further, in a few weeks, a copy of today's webinar archive will be posted on the same website. And with that, I think that ends the logistics part, and I'm going to introduce our speaker today. Our speaker today is Tim Wohl, and Tim is a national TMDL expert with US EPA Region 4, located in Atlanta, Georgia. Tim has over 25 years of experience in the development and application of water quality models that are used for TMDL development and waste load allocations. Tim established the Watershed and Water Quality Modeling Technical Support Center located at EPA's Office of Research and Development Laboratory in Athens, Georgia. Tim is one of the primary developers of EPA's Water Quality Analysis Simulation Program, WASP, which is routinely used in the United States and throughout the world. And with that, I'm going to turn the presentation over to Tim.
Today's webinar is going to present the data needs for applying watershed and water quality models. The objectives of the webinar is just to provide an overview of the types of data that are needed for watershed models, hydrodynamic models, and water quality models. We'll discuss methods available to retrieve data, whether it be online or via local, state governments, provide examples of tools to process retrieved data, and then in the end just show you how to organize all of the data that is needed to apply a model. So the types of data that we're going to discuss are going to be meteorological data, physical data, which could be things like stream geometry, lake bathymetry, so on and so forth, flow data, water quality data, chemistry data. For watershed models, you need to pay attention to the time scale at which forcing functions need to be applied. For the examples here, for hourly forcings, which basically means that the model is expecting to have hourly meteorological conditions throughout the simulation period for HSPF and LSPC. For tools like SWAT, it's daily forcing, so it expects stuff to be done on a daily time scale. And for more simplistic watershed models like the Generalized Watershed Loading Function model, GWOLF, it makes annual calculations, but you can give it things like daily daily rainfall. When it comes to water quality models, it too has a set of forcing functions that has to be consistent with the data that you provide it. For models like WAS, SQL W2, EFDC, and all the other time variable continuous simulation models, they pretty much allow you to specify the forcing functions, whether they're meteorological, flow, or chemical conditions at virtually any time scale over the simulation period. Another type of model is a steady state model, such as Qual2K. Now, this model requires you to provide a specific set of data at a specific time for the model to do its calculation. So it's a single set, usually a critical condition. All right, let's look at the data requirements for watershed models. What we're going to do is we're going to go through the major data components for watershed models, where you can get it from, and then later on in the webinar we'll show you how you can download it and process it for use in the model itself. The first data component that we're going to look at for watershed modeling is the land use coverage for the watershed. We typically get this data from a national database called the National Land Cover Data Set, which is maintained by the USGS, and it's updated every 5 years. There's always a lag in when it's available because it takes a good bit of time to process all of the imagery for the United States. But currently available, you can download the 2011 and 2006 land use coverage. The 2016 coverage will be available shortly. Another good source for land use coverage data would be state and local governments. Many times they keep their coverages up to date because they feed directly into their planning and development process. What the land use coverage does is it breaks down the watershed into individual polygons that represent a specific land use category. The number of categories and how they're aggregated you can control through GIS processing. But what we get in the watershed model is for each one of these land use types we can control or define the pollutant load contribution by a particular land use type. In the watershed models it's done through several different mechanisms. The most commonly used one is something called build-up and wash-off, which for each individual land use type there's a different rate in which pollutants build up on the watershed as a function of time between rain events, and then there's a function that you can use to define how much of the pollutant that built up on the individual land use types would wash off. You can even, for agricultural processes, you can actually put in fertilization rates as well. That would be part of the build-up and wash-off. And another method for doing it is something called event mean concentration, which basically you would assign an average concentration of a pollutant coming off of any particular land use type. So there wouldn't be a build-up and wash-off component. It would actually just be a constant concentration when there is runoff. A separate coverage that could be downloaded from the NLCD site is impervious cover. Impervious cover is the areas of the watershed where it is impossible for water to infiltrate into the soils. So this represents any water that falls on an impervious area would run off, and it would also carry with it whatever pollutant load contribution that was assigned to that particular land use type. Typically you have to combine the land use coverage and the impervious coverage into one coverage before you process it into hydrologic response units for the watershed model. The next data component you need for watershed modeling is a soils coverage. The soil coverage is used to provide information to calculate infiltration into the soils and groundwater. There are two sources readily available for soil coverages. The first one is SURGO, the Soil Survey Geographic Coverage, and then the State Soil Geographic Coverage, StatsGo. These coverages don't change. They are available for download from the web and are readily available. The next data component you need is the stream network component, one that represents the stream collection systems for the watershed. With a watershed model, there's two methods of defining the reaches for collecting the water. It could be calculated and derived by using the digital elevation model, or you can use a stream river network coverage. One of the most popular ones used in the United States is NHD+, which is developed by the USGS and which represents all of the hydrography in the United States. And then you also could rely on special studies done by municipalities, surveys specifically to the modeling task at hand. The next data component for watershed modeling is assembling the meteorological data. And by far this is the most daunting task in setting up and using a watershed model because of the vast amount of data that you need to successfully apply a watershed model. And typically that data is not in the format that's needed by the watershed models. And one of the big issues with watershed models is they all have their own different file format and structure that's used to feed meteorological data into the model. But the type of data you need is you need hourly rainfall, solar radiation, air temperature, wind speed, dew point, cloud cover, and evapotranspiration. And all of that is going to be provided in whatever time frame the model needs. For a model like HSPF, it's hourly. Typically, you'd have to process this data to make sure that there are no gaps in the data, and if there's gaps in the data, you would have to go back and fill them in from data from other stations. So it's a tough task, and the other issues that you have is making sure that all of this meteorological data is transformed into the appropriate units that are needed by the watershed model. There are several locations for downloading meteorological data. The most prevalent ones, of course, are is NOAA's National Centers of Environmental Information. Both NCDC and the GHCN weather station data is available for download. There's some issue with their data being readily available and free to the public for downloading. So it really depends. If you go in there with a .gov extension, you can download data for free. Another source of data is data that's been developed and processed by NASA called NLDAS, and this data is readily available and can be downloaded from the internet, and it'll provide the hourly information. And then there's also specialty research and agricultural meteorological stations that could be in your watershed that are used for controlling irrigation and things like that. All right, moving on to water quality models. One of the nice things, if you have developed a watershed model to provide boundary information to a water quality model, when you gathered most of the data you needed for the watershed model, it can actually be used in the water quality model as well. So what we're going to look at now is the specific data needs that water quality models require. The first step in developing a water quality model is determining the spatial domain that the model is going to be applied for, and then developing a segmentation or a model representation of the system that you are simulating. So in our case here for rivers and streams, we would be setting up a model for doing the fate and transport of a pollutant in a riverine system. Our primary sources for developing that segmentation or model network would be NHD+, the National Hydrography Data Set by the USGS. It provides detailed stream geometry information as well as conductivity information, so it knows you can trace up an NHD network and pick up all the tributaries that come into it. You can use site-specific survey data. It could be field exercises conducted by an agency or a local group. You also can access the FEMA flood maps. A lot of them have detailed cross-sectional information that they use to put into the flood models. Or in some cases, you could be linking the water quality model to a hydrodynamic model, which would already inherently have the model network built within it. If you're simulating lakes, reservoirs, or estuaries, you're going to need to find bathymetric data and also develop relationships between depth and volume, depth and surface area. Most of the data for lakes, reservoirs, and estuaries is not readily available from a single data source. Typically, you got to go to site-specific sources to find specific data. Bathymetric data for reservoirs and such can be found at the Corps of Engineers or TVA or whatever authority is operating the reservoir. For estuaries, NOAA navigational charts can be used to develop bathymetric relations. The next data component that's critical to applying a water quality model is boundary data. Boundary data is defining anything that comes from outside the model network in. So it's defining the flows at the starting points of your network, as well as the pollutant concentrations that are coming in with those flows. It's very critical to understand your boundaries and parameterize them appropriately. Not knowing what your boundaries could lead to a miscalculation using the water quality model. So the first set of data we would talk about is flow data. This would be the flows coming into the model network. We can get our flows from direct measurements from the USGS gauging stations that are in the watershed or adjoining watersheds, where we can make area weighted calculations or other calculations for estimating flows where you don't have gauges from areas where you do have gauges. There could be special studies that were designed to capture or measure flows at certain conditions or for continuous simulation. Or in a lot of cases, you use a watershed model to provide daily flows and concentrations that are boundaries for the water quality model. The next component would be the water quality data. Sources of water quality data are EPA STORET database, the USGS NWIS database. You could go directly to the states to see if they have additional data. Sometimes dischargers will collect both upstream and downstream water quality above their discharge point within the water body. That could be used to help parameterize a model, as well as stakeholder or third-party data collection within a watershed. It's critical to survey the kind of boundary data that you have before you select a modeling approach or a model to use for water quality. Just like watershed models, water quality models make use of meteorological data as well. Rainfall for water balance, solar radiation is used for phytoplankton biomass kinetics, air temperature, wind speed, and dew point, cloud cover could be used for calculating water temperature. It can be used for calculating reaeration. So all of the same data that you downloaded and processed for a watershed model would be the same kind of information that you would process for the water quality model, and actually could use the same steps. All right, we're just going to talk briefly about the type of data that's needed to set up a hydrodynamic model. It takes much the same kind of data as a water quality model and a watershed model. But the first thing you need to do is you need to be able to define the spatial component or the model network area that it's going to encompass, and be able to define the hydrography or bathymetry to the model. So we can use the same data sources that we use for marine components, the NHD+, and then for lakes, reservoirs, and estuaries, we can use bathymetry or navigational charts, and then if there's site-specific survey data, it could be used as well. For boundary data, we are going to have to be able to provide flows and loadings to the model, and those flows and loadings could be either modeled or measured. The typical loading function, quality function that a hydrodynamic model needs is anything that would affect water density. So in most cases, that's temperature and salinity coming into the water body. You would need to have measured water surface elevations down at the seaward boundaries. This would be your tidal elevations. And other sources of potential data for the boundary would be from state or stakeholder monitoring. The hydrodynamic models does calculate or predict water temperature, so it pretty much uses the same meteorological data as the watershed models based on an hourly time interval. The next set of data, which you would probably need whether you're applying a watershed or water quality modeling, is point source data. And this could be almost an arduous task as processing meteorological data, just because the amount of information that is available, how you have to get it, and sometimes the assumptions that you have to generate so that it can be used. So when it comes to the point source data, there are several different ways that you can get NPDES permitted discharge data. Typically, it's available in two forms. One, the readily available form, is called the DMR, which is the monthly reported values. And this typically is a requirement of their permit. And that data can be found in several different places, whether it's EPA's ISIS, the Integrated Compliance Information System, which isn't directly open to the public but can be accessed by either the state or a federal agency, or ECHO, Enforcement and Compliance Data, which is available via web services to the general public. But typically the best way to collect and bring in point source data is work with your state and or the point source discharging facility to obtain their data. The DMR data, the monthly reported values, typically is one value per month, but they use this the MOR data, daily values maintained by the facility, to calculate the DMR data. So you could go to a facility and see if you can get the MOR data or the multiple collections that were used to calculate the DMR and use that to populate and characterize their discharge in the water quality model. The next set of point source data is municipal separate storm sewer system data, MS4, which is a diffuse loading, and typically there doesn't exist very much monitoring data, but the only way to get this data is to work with the state or the municipality to get whatever data they collected. Typically in water quality modeling exercises where there's MS4 components, it is done with a watershed model to provide the flows and loads to the water quality model. The next set of data that you're going to have to compile and get together is the data that you're going to use for model calibration. This data should consist of any of the state variables that you're calibrating in the water quality model or the watershed model, including flow. The sources of this data could be, for flow data, it's going to be the USGS flow gauge network. For water quality data, you're going to go to the water quality data portal where you can access the NWIS data as well as the STORET data. Get any and all information you can get from the state databases or local governments, or if there's any special studies or any data collection activities that occurred through the stakeholders or third-party data collection. There are many challenges when it comes to assembling and collecting and organizing data. First and foremost, we're collecting this data to apply to a water quality or a watershed model to help aid in a decision, whether it be a watershed protection plan, TMDL, waste load allocation, so on and so forth. The data that we collected, we have to understand, is going to be shared with everyone that's involved in the process, so everything is an open record. With meteorological data, you will spend a large portion of your time processing meteorological data. When we're running these continuous simulation models, typically we're running for 6 to 10 continuous years to account for varying meteorological conditions. The meteorological data has more data formats than virtually any other data source that we deal with. So being able to process the data in their various formats, as well as converting them to the appropriate units for what the models require, is a critical time-consuming step. For periods of time we have large data gaps, you have to go in there and patch those stations, because if you have stations that have large periods of time where there's no rainfall, that subbasin that's assigned to that meteorological station will have no input until it rains. Point sources, typically there's limited data to characterize the waste stream. It's simple. Most of the time it's a couple of different parameters that ultimately you'll have to translate into what the model needs. An example would be they could be measuring total nitrogen and total phosphorus, but yet the water quality models need them in ammonia, nitrate, organic nitrogen, or orthophosphate and organic phosphorus. And again, there's going to be data gaps, and sometimes from permit to permit the sampling parameters can change. When it comes to the ambient water quality data, assembling that and looking at what kind of data you have, what's the spatial and temporal domain that you have is a challenge, but you need to make sure you understand it. And you need to understand that more data does not correlate actually to a better calibration. An example would be if you look at a system here. This is Mobile Bay in Alabama, and this is after doing a STORET pull everywhere that you have a red dot there, that means you have a water quality station, which means it's indicative that you have some data associated with it. And it looks like it's a lot of data. But really, when it's all said and done, there's not much information here, because once we call out and say, okay, well, show me the number of stations that have more than one sample, these are the stations. So we go from having a lot of data to some stations that have data that actually gives us information that we need to successfully apply a model. Clearly, one of the first things you should do before you apply a model is to collect and survey all the available data that you have. Look at what the data is trying to tell you as far as trends, as well as how well can you represent the water body with the available data. With that, we're going to stop right here for a moment to take questions on data requirements for models. Now we know the types of data that are needed by watershed and water quality models. What we're going to talk about now is how we can access this data, where to get it, and how can we process it to put it into a form that can be used by the models. The tools for accessing data that I'm going to be discussing today are EPA's Basins 4.5 Core, accessing the Water Quality Data Portal, which is a shared web access between USGS, EPA, and USDA. The Water Resources Database, which is a public domain tool, database tool that has the ability to download and process data. And then some simple R utilities that we use typically to download data. All right, the first tool I'm going to talk about is Basins, the Better Assessment Science Integrating Point and Non-Point Sources. It's a public domain geographical information system that was designed to support modeling and watershed characterization, source assessment type tools. Its primary purpose is to collect or assemble data from various sources, process it into a form that can be used by assessment tools and water quality models. It also has the ability to have third-party or even EPA people develop plug-in tools that could use this data to build at least initial model input data sets. Alright, I'd like to give you an introduction to Basins, and then we'll show you how we can use it to download and process data. We're going to be looking at Basins Core 4.5, which was released earlier this year. What we're going to be doing is we're going to be creating a project. We create a project by selecting an 8-digit hydrologic catalog unit somewhere within the United States. If your water body or your area of interest is smaller than that, you have to download the HUC8, and then you can break it down into smaller components. We're going to talk about setting up a base projection, the Geographical Information System projection. Doing so would make it compatible with ArcGIS and tools like QGIS. Alright, then I'll take you through and demonstrate how to download data. And the type of data that we'll be downloading would be pre-processed meteorological data, the NHD Plus National Hydrography data set, USGS NWIS data, the National Land Cover data set, and then the North American Land Data Simulation System. We'll download each one of them, and we'll talk about what data is in each one of those data sets and in which models it will be applicable to. Some of the model plugin tools that are available to work with Basins 4.5 is the WASP Model Network tool, a tool for developing an initial SWOT input data set, one for building a SWIM model network, one for setting up and parameterizing the general watershed loading function model, a tool that processes information that you can put into the pollutant loading model, which is a simple spreadsheet model. Most people know it as pload, and then there's a climate generator tool that you could use for looking at different climatic conditions. Alright, with Basins, once you download it, you will need administrative rights to install the program on your computer system. You will also need to have an active internet connection to interactively download the data. What we're going to start with first is we're going to build the Basins project. The Basins project is the thing that defines the area in which data will be downloaded for. It doesn't try to process or download data for the whole United States. It does it specifically on a HUC 8 coverage. Okay, once you've successfully downloaded basins, you would load the program by just hitting the Basins 4 link. We're going to build a new project, so select Build New Project, and you'll get a HUC 8 coverage of the United States. At this point, you would have to zoom in to the HUC 8 that you're interested in, so you have to have a good idea where it's at. In my case here, I'm going to Georgia, and I'm going to select the Upper Chattahoochee HUC, which is just north of Atlanta. You can see I use the selection tool, and I say Build. And now it's just asking me where to save my information. I like to create directories for each one of my projects, so I'm going to create a folder called Upper Chat. And then I'll also name my project file the same thing, just so that I clearly know what is here. By default, Basins uses the HUC 8 number. I can never remember a HUC 8 number. So once the project is created, you'll have the ability to pick a projection, a geographic projection, and you can pick any one of these. They're compatible with ArcGIS. Once the projection is selected, it actually goes out to the internet and downloads a set of base coverages that will be the basis for our basins project that we'll work on. So in our case here, it went out and it's gotten a couple sets of coverages. One is a PCS, or a permit coverage. This could be, this may not be up to date. There may be some inactive or active, or ones that aren't available. We have a reach file coverage, county coverage, road coverage, and a StatsGo soil coverage that you could use in your watershed model instead of StatsGo. So that's how you build a project. Before doing the demonstration of the Basins download capabilities to assemble data, just quickly want to just give you an overview of how it works. To access the data download, you go to the File menu and you click on Data Download. That'll bring up a dialog box that looks like this. And basically, this actually controls how things are downloaded. The first thing is you have to specify the region in which data is going to be downloaded for. Typically, we use the hydrologic unit coverage. That would be the polygon that was selected when we created the project. But you can also do it by the view rectangle, which would be, you know, what the four corners of what's actually on the screen at the time you do download. You could do it to an extent of a selected layer, or you can enter coordinates of the corners, or even down by station ID. So that's kind of how you select the area that you want. So the first thing of data that you could download is up at the top here, and really the only one I want to call your attention to, because all the other stuff is so old that it's probably not worth downloading, and some of it actually may not even work anymore. But you do have the ability to download pre-processed data. In particular, it's going to be meteorological stations. These meteorological stations were processed by a contractor several years ago and put into a WDM file format, which is the meteorological file format that HSPF uses. Its biggest drawback is it only contains data from 1997 to 2009. So you can use this as your basis for some of your projects, but you may have to go out and get additional data and augment this. So once you select the stations, it will download a stations coverage, and you can pick any one of these stations and download data, and we'll demonstrate that shortly. The next thing is you can download the National Hydrography data set, and there's 4 components that you could pick. If you pick all, that means you're going to get all of the coverage that's associated with the NHD Plus coverages, or you can just pick the digital elevation grid, the catchment grid, which is basically the drainage areas, the sub-basin drainage areas within your watershed, and then the hydrography would be the flow lines. And you can download either NHD Plus version 2.1 or version 1. I would suggest you download the 2.1. This is the most up-to-date coverage. And when you download this thing, you will get, this is what the NHD catchments look like within the system. This is what a hydrography coverage looks like. And then this is what the digital elevation coverage looks like. And again, we'll talk more about these as we download them dynamically. The next thing that you can download is USGS NWIS data that you can get flow discharge data, water quality data, measurements, daily groundwater, and some periodic studies. The first thing you need to do is you have to pick the type that you want to download. So in our case here, we're going to just look for USGS flow gauges, and it'll download a coverage of the USGS gauges that are available in your watershed. You would select the individual stations that you want, and then you would download the data, and it'll come into your basins project, and we'll talk about the different ways once I demonstrate it of how you can store that data. The next coverage you can pull in is the National Land Cover Data Set, and currently right now 2011, 2006 are available for dynamic download. The 2016, as I mentioned in the previous earlier parts of the presentation, should be available shortly, and this will provide you with the land classifications for your watershed and your impervious area for your watershed. And then the last thing that we can download is the North American Land Data Assimilation System. This is basically meteorological data that could be served up, and it'll provide you a grid of where the data is available, and this grid is I believe 30 kilometers, based on 30 kilometers, and it is developed by NASA, and it provides hourly meteorological data conditions based upon using radar data. Once you select the grid option, you'd be given a coverage. You would select whichever grid center you want to download the data, and once you download the data, it will put it into a format that we can process later. You'll also notice that there's a UTC offset, so we can calculate the local time based upon Greenwich Mean Time. Alright, the first data download I'm going to show you is how to download that prepackaged meteorological data in the WDM format that covers the 1997 through 2009. We're going to go to the File, Download Data, select MEC Stations, Download, and it's going to bring down all of the MET stations that are available for here. So this just gives us the station coverage, and you can tell based upon the icons here what kind of data is available at each one of those stations. So I'm going to just use the selection tool with the weather station site highlighted, use select, and I'm going to select these two right here, and then I'm going to go back to the data download tool and say download data, and now it's going to say metadata, download, and now I have the option of storing it in a WDM file or something else. I'm just going to put it into a WDM file. I'm going to click OK, and that data has now been downloaded, and it's in the WDM file, as you can see right here. So that's how that works. Alright, the first coverage that we're going to download is going to be the National Hydrography Data Set. So we're going to go to the File Download menu. You'll see we have our choice between version 1 and 2.1. We're going to download all of the coverages at once. We'll click All, click Download. Basins will go out to the USGS server and download the information, and we'll project it into our project. So now we have all of those coverages here. So we can just clean up and just look at a couple of them before we move on. And the first one is we're just going to look at the flow lines or the stream network, and we can actually clean up this so we can see it a little bit better. So we'll change the color of the river segments by just clicking on its coverage and then going to appearance, and we'll just change it to like a blue, a more natural color for a stream network. So that's the stream network from first order to the largest order. This is the catchment coverage, which is the drainage areas based upon the DEM. You can use these to help define your watershed subbasins. And then the last thing that we would look at would be the digital elevation model, the DEM, which displays the elevation of the land surfaces that could be used for calculating the slopes in the for the watershed model, as well as the slopes for any transport water quality models. So that's the NHD plus. Okay, the next step is we're going to download the National Land Cover data set. We're going to get the land use data first before we get the impervious area. So again, going to the file download, we're going to click on the 2011 land cover data. It's going to go out to the USGS server and start to download. These files can be fairly large and it may take a little while for them to download. Okay, once the data is downloaded, it's projected into our system, and you can see now that it's showing the different land use classifications for the rectangle that we downloaded. The USGS server does not do it by the HUD coverage. Okay, we've successfully downloaded the National Land Cover dataset. Now we're going to go back to the USGS server and download the 2011 impervious area coverage. Again, the same process, going out to the USGS server to download the data that we need, and it'll project it in this project. Okay, so the data has been successfully downloaded and processed into the Basins project. You'll notice that this extent is the same as the NLCD. Our next data download function that we're going to look at is downloading the NL-DAS meteorological data. Again, go to the data download tool, select grid, and it's going to bring down all of the grid points in which we have data that was been processed and prepared by NASA. I'm going to go ahead and activate the coverage that was downloaded. So we get a grid point. So we can get hourly meteorological data at any one of these points, and you can download as many as you want. You download these stations much the same way you download the NWIS data. Select the stations that you want. So I'm going to activate the layer, and I'm going to use the selection tool, and I'm going to select, in my case here, I'm only going to select 2 grid points. And then I'm going to go back to the download script, and it's going to say download the data. I'm going to set the UTC offset to -5 for the eastern United States. I could save this information either into a WDM file or into a separate file. I'm going to leave it in a WDM file for us for here right now, and I'll show you different ways that we can get data out of a WDM file later. So now it goes out to the NASA server, and it's downloading the data. This process here could take a good bit of time because it's downloading the information from the website, but then it's also processing and putting the data in the WDM file as it goes along. So please be patient while this is going on. Okay, it successfully downloaded the data into the WDM file, and it's ready for our use. The next set of data that we're going to download is going to be the NWIS USGS flow data. And this process works for everything. So the first thing we're going to do is we're going to download the locations of the stations. Basins goes out to the NWIS server, comes back with a coverage of the stations. I'm just making them a little bit bigger and going to change the color of them here so that we can better see them. Because ultimately, how we retrieve the data is by selecting the stations that we need the data for. We could go get all of them, but in my case here, I'm just going to zoom in a little bit, and I'm going to select a couple of stations to download. And you just basically, with the shapefile selected over in the cataloging unit, you just use the selection tool to select the stations that you want. I'm just going to pick 3 stations on the Chattahoochee River, and I'm just holding the control key down and selecting the 3 stations. Then I'll go back to the data download system, and now you'll see that we can go ahead and get the discharge data, and it's going to go out. Now I have the option of saving this in a couple different formats. You can add it directly to a WDM file, which HSPF can access. In my case, I'm going to save it to an individual. Each gauge will be saved to an individual station in the USGS RDB file format, which can be read by several different programs, including Basins itself. And we'll see some demonstrations of that later. So once it's down, you can see that Basins brings up a data catalog, and it shows that the 3 gauges have been downloaded. All right, once we've assembled all the data inside Basins, I'm going to show you another tool that we could use to do a characterization of a watershed. In our case here, these 3 polygons could represent 3 subbasins that are going to be used in a watershed model. And what I'm going to do is I'm going to have the system give me an analysis of each one of those individual polygons for land use, and then tell me about the other available data that's in there. So I'm going to activate the watershed characterization system from the Analyze screen. I'm going to ask it to use my polygon coverage for the subbasins, which could be equivalent to a subbasin coverage that you develop for a watershed model. It's going to report and tell me for each one of those polygons the land use categories, the area that's associated with each land use category for each one of those subbasins. It'll also give me any information about permitted point sources in that area, and then just summarize any of the data, the time series data that we downloaded from the internet. Okay, so it's completed and it's generated this report. So let's have a closer look at this report. So we have in this column here, this is the land use report, the 3 subbasins that are labeled 0, 1, and 5. And then these are the land use categories that were found in that individual subbasin. And then this is the total area of each of the land use types for each one of those basins. So this is the kind of information that needs to go directly into a watershed model. They need to know the area associated with each land use type. Then you would provide the pollutant loading functions for it. And then this just gives you a summary for the whole subbasin, just in a table format of each land use type and the area associated with it. This is a list of the point source data set, point source discharges that are in the area. And then lastly, this is the time series data that we have downloaded and processed so that we can use in this project. There's our USGS gauges. Here's our NLDAS data, our rainfall data that we could use to drive the watershed model. This file is actually available and stored in your Basins project, so you can refer to it at any time. And you also can cut and paste directly from this screen to a spreadsheet. So that's the watershed characterization system. It does more, but that's the most important thing, and that's how it processes some of the data that we download for watershed models. The next method we're going to look at for obtaining data is to use a website. The website is the Water Quality Data Portal. It is a web-based system for water quality data. The databases that you can access here are EPA STORET, USGS NWIS, and the USDA Stewards database. So you'll see in the demonstration that you can download data from anywhere in the United States where that data exists. A couple of words of caution are when you're pulling EPA STORET data, there aren't a lot of rules or filters that each state has to adhere to, so you have to pay attention to the parameter codes that you're downloading to make sure that you fully understand, like ammonia is ammonia as nitrogen, and not measured as ammonia. And you'll see when we go through how do you process this data, we have developed a couple of tools that make it a little bit easier to do this, but you have to have a little bit of caution when you do a portal pull and use the data. All right, now we're going to look at a method that we could use to download both EPA STORET data, NWIS, USGS NWIS data, and USDA Stewards data. And we're going to go to the Water Quality Data Portal, which is a shared resource between all of those data providers. And there's many different ways where you can select the area that you need your data for. I'm just going to enter in my HUC 8 because I'm just going to ask it to get me all the data that's available for my HUC 8. This way I have an idea of what kind of water quality data is available for the whole watershed. And then you can actually set different components. I'm setting my media to water. You also can use characteristic groups if you wanted just nutrient data, physical, chemical data, pesticide data, so on and so forth. You can have it subset based upon that characteristic group. I'm just going to leave it set to all. And then I'm going to set the time frame that I want data, January 1st, 2000 through 12/31/2018. So that's the period of time that I'm going to ask for it to tell me or give me the data that's available. And then the last thing I'm going to do before I actually make it do something is I'm going to ask it, I'm going to tell it which data sets I want. I want the NWIS, USGS data, and the STORET data. And this is what's going to happen now is we're going to pull down a comma-separated value file. The first file is just going to be our site characteristic data. So this would be station ID, station name, the agency, the lat long, what kind of sampling gets done there. And it's all going to come down into a comma-separated value file. So it just returned to tell me how many stations were available. And now I'm going to click continue. And what it's going to do is it's going to query those stations out, create a zip file so that it can be downloaded to your computer. So here it's asking us where we want to save the zip file of the station information. It's called stations.zip, and it's zipping. It zipped it up, and now it's been sent down. Our next step is we're going to want to return the sample results, and there's other metadata that you can download as well. But our primary concern is going to be with the sample, the results, the observation, the measured observations. And that's by clicking here, and it does the same thing. It's going to go out and do a query. It's going to tell me how much data is available from the STORET system and the NWIS system. So there's the number of observations that are available from each database, and it's going to do the same process. It's going to query the data out. It's going to create a result zip file for us to download to our system. Once it's completed download, it's going to ask you where to save it. We'll talk later about how to process this file, but this is how to obtain the data. I'm going to demonstrate a utility that we can make available for processing data that's downloaded from the Water Quality Data Portal. As you recall, we downloaded two files, a results.zip file and a stations.zip file. To use this utility, you would basically unzip the stations table, the CSV file, and just insert it into this tab of the spreadsheet. And then you would put the data, the results, into this tab. You can just read it in or cut and paste it in. And then this program has the ability to process and pull out whatever STORET codes, P codes that you want, or USGS codes. And it basically you just bring it in, you tell it to process the stations, and it'll run through the list and come up with a valid list of stations. And then you would go on, process the P codes. It would find all the unique P codes in there, compare it to the P codes that you want to process because you need it in your modeling exercise. And then the last thing is you would process the STORET data and the USGS data. In our case here, again, all of the processed data is going to go out into a CSV file. Ultimately, this is going to go to the Water Resources database, but you could just pull the processed data back into a spreadsheet or whatever tool you want to use for your modeling exercise. And it's going to create a CSV file of all the stations with all of its metadata, a parameter code file with all of its metadata, and then two data files which will have the STORET data and then the USGS data. As it continues on and processes the data, we're just going from one button to the other to process each individual data set to get ready to go to the Water Resources database. So just to summarize, we just processed, there was 547 stations. The number of P codes that we processed out is 52. The number of STORET observations that we processed is 81,787. We discarded close to 60,000 of them because they were parameters that we weren't interested in. And then here's the USGS that's been processed and the USGS that has been discarded. And in just a little bit, I'll show you how we could just pull this data directly into WRDB, and we could use it for modeling purposes or data assessment. Another good method for retrieving USGS data is to use R-based tools. The USGS has developed several packages that makes it very easy to download data from their data service centers. It's easy to use, it's very fast. And the types of data that we can get are the USGS flow gauges, access to their continuous data or their SON database, where they have water quality SONs deployed, where you can get 15-minute water temperature, pH, DO, conductivity data. And once you get the data into the R packages, I mean, R has a lot of capabilities for doing plotting, to do statistical analysis, and more importantly, data manipulation to get it ready to go into the model. So I'll just show you a quick demonstration of some simple R scripts that we use in Region 4. Okay, I'm going to just a little overview of using R to retrieve data. As I mentioned before, the USGS has put a little bit of effort into building R packages for data retrieval. So basically, I'm giving it my 3 USGS gauging stations that I want the data, the parameter codes that I want, and then the time period that I want to select data. So basically, this is just parameterizing this R code. I'm just going to go ahead and run the R code. There's 3 pieces to it right now. Hopefully in the future it'll be cleaned up a little bit more, so it's a little bit easier to run. But it's going out to the using the USGS data retrieval methods, and it's pulling down the data. The data is actually coming down in a comma separated value file that, again, you can do whatever you want with. In our case, we'll be pushing it forward into the water resources database, but also it's creating some plots so we can just quickly look at the data. So here's one of the gauges that we pulled down for the 2000 to 2018 record. Here's the next gauge that we pulled down, and then our last gauge that we have data for. Okay, we're going to pause here for some questions about downloading data. The next portion of this webinar is going to show you various tools that will allow us to process that data, visualize that data, and get it organized and ready to go into a modeling package. So with that, let's stop for questions.
All right. Just a reminder for everyone to get your questions typed in. We'll I think we have this question and answer session and one more at the end. We'll try to get to as many as possible, but as you see, we are running a little bit short on time, so I might limit some of these. So Tim, I'm going to go back up to kind of where I left off on the questions, and one is a kind of a general question about what kind of support does EPA provide for basic hydrodynamic and water quality models on our various web pages. And the question the asker is specifically asking about WASP and EFDC.
Yeah, so I would be the one that would provide support for WASP. There really is nobody to provide support for EFDC. I would try to answer questions if I can. Unfortunately, there's nobody dedicated at EPA to do any of that. I actually have a regular assigned duty, so I try to get to as many as I can. But there is no formal area. We do have, if something that has some importance to it, we do have our water modeling work group that we may be able to find a way to get somebody to help with a modeling question.
Okay, next question. I don't know if I don't think you talked about atmospheric data. If you were looking at things like nitrogen or atmospheric deposition, where might you look to get some of that information?
Yeah, so there's several sources for atmospheric information. There's a national atmospheric deposition monitoring program in the United States, and if you just search for NADP, you will find that, and they actually have data that you can download that will give you time series of atmospheric deposition for several different pollutants.
Great, thanks. Next question. I was wondering if you'd want to just say a little bit more about basins in general. I think there's a new release that just came out or is coming out, and how that's supported at EPA.
So yes, the thing I'm showing you is available from EPA. It was released, I think, in end of January. It is currently being supported by EPA, at least, trying to keep it up and running and keeping the links available. The primary person that's been responsible for that, he's actually been answering a lot of the questions online. He's not in the room with us, is Glenn Fernandez here in Region 4. Our goal is to keep it going and to try to build some more components in it.
And another basins question, can the information you pulled into basins that you demonstrated, can that be then just put into a regular old GIS, whatever you might be using, ArcGIS or QGIS or whatever?
Yes, so any coverage that you download with basins, it will create the projection file, which means that you can pull it into any GIS system that supports the general formatted PRJ file.
Great. In the example that you presented, the question says it looks like there's a reservoir somewhere in the watershed that you presented, and maybe just talk about how the model, or the setup at least with the data, deals with releases from the dam.
So that reservoir is Lanier. It's the largest reservoir in Georgia. There's a gauge right downstream of the dam, so we would have the measured releases from the reservoir. There are water quality and watershed models that are set up for Lake Lanier, a hydrodynamic and water quality model, as well as a watershed model to help manage it. So again, a lot of the data that you downloaded here would be used to parameterize a watershed model, and then the inflows to Lake Lanier itself. You would be using a hydrodynamic model and a water quality model for impacts in the reservoir itself.
Thank you. Next, regarding the tool the data processing tool you presented, there were, I think, a couple of questions about could people get a copy of that. Is that posted somewhere, or how would they go about obtaining that, or is it publicly available?
It is, and I think what we'll do, Jason, is we haven't had a chance to talk about it, but when the webinar is posted on the YouTube site, we'll put the links into where you can download the data. If anybody wants to get it sooner, they can just email me, and I will send it to them.
Great. And I was going to comment, I know Tim's presented a number of different tools here today, but, kind of an overview and very quickly, I think almost all of those tools have a variety of training packages, FAQs, etc. online that I would encourage people to go look at, users guides, etc. So if you want more information on basins or the WQX portal or the tool Tim is building, the pre-processing tool or whatever, just look around on Google first. I think there's a lot of information out there, including R. I do know there are a number of free training courses for R as well online. Scrolling down here. You talked about some of the R packages with USGS. How would people go about getting that, or what is their name?
The primary one's called egret and data retrieval. So if you just Google USGS R packages, there's a whole host of them. They actually have an R package for their low flow analysis, or their 7Q10 flow analysis. It's an R package that you can download as well. And it is by far the most efficient way to go pull data from the USGS. It's the R demonstration I showed you, there was no speed up there. That was done in real time. When we were running that stuff, it went out and pulled the data down, processed it, and it was on my machine.
Great. And then maybe last question for now. What format types are available for some of this, like for example, gauge data that you downloaded? And when you download something in basins, for example, or WQX, for example, can it be used in other programs?
So that's the next part of this thing. I'm going to show you how you could pull it in. A lot of this stuff, the USGS gauge data, when you pull it down in basins, comes down in basically one format, the RDB file format, which is a tab delimited file that you can pull into Excel and process. If you elect to do the WDM, Basins just reads that file and puts it into a WDM file. And then you'll see some utilities in a little bit that'll show you that it knows how to read an RDB file. And then I try to, with our tools and most of the tools out there, we try to use the common comma separated value format for most of the time series data, so people can use whatever tools they want.
And with that, so let's continue on.
All right, let's talk about processing and organizing the data for modeling. I mean, this is probably the most critical step in this whole thing that we're talking about today. Assembling and getting data is a time-consuming process. It takes more time to actually process it, make sure it's the correct data, and getting it ready to bring forward into a model. So processing is critical, and then organizing the data so that you clearly know where the data came from and how it goes into the model. So when it comes to processing the data, you should first process the data into a format that you're familiar with, whether it's a CSV text file, what ultimately goes into Excel, which is what most people do. Excel is a great tool for organizing data. If you want to, you can create your own database system and store the data in a database. Again, another great way to maintain data. But as you're processing and moving data in, it's important to maintain the metadata. Where did the data come from? And if you did anything to it, what did you do to it? Did you convert it? So on and so forth. And then you also need to check the data. You need to do a quick QA, QC on the data to make sure it is the data, you got the data that you expected. Analyze the data for any data gaps. This way, if there are data gaps, you can look to ways to fill it or understand that you have some missing data. Then organize the data for modeling. Assemble the data into a project file by data type. And what I mean is you have a folder on your computer that's your project, then a folder that's data, and then you can have folders underneath that: meteorological data, land use data, flow data, water quality observations data. You're going to have to do some kind of data conversions because not all the data that you download are in the units that are expected by the models. So you'd have to do that data conversion. And then ultimately you would have to move the data into the model itself, whether it's cutting and pasting, typing, or querying the information into the model. That would be your last step. Basins includes a data viewer that will allow you to look at the data that you download via its processes. The data processing that occurs, it allows you to manage the downloaded data. You can look at the meteorological data, the flow data, any observed measurement data that you have. You can view data in a time series format. You can have do statistical analysis, seasonal analysis. So it has a lot of built-in tools. It's kind of very rudimentary to use, but it is functional. Another utility that's available that can look at Basin's output file as well as WDM files is the Sarah time series utility, which is something that was developed outside of Basins, but pretty much has the same functionality, but just a little bit easier to use. All right, let's have a quick look of how you can look at some of the data that you downloaded just using Basins itself. It's a fairly simple process that it has. It doesn't do a lot of analysis for you, but if we just go to Manage Data, and we can say Analyze, and in this case I'm just going to create a graph. Now I'm not going to do it for all 27 data sets, but I'm just going to go and get one of our USGS flow gauges, and we can see we can do things like time series flow durations, frequencies. You can sum data, which would be critical for like doing rainfall analysis, do differences between two data sets. You can do a scatter plot, one versus another, so on and so forth. So I'm just going to tell it to generate a time series data, and so there's our graph of our flows that we downloaded. So it has kinds of functions like that. The basin's data management system is better suited for putting information into HSPF more than anything else. Some of the other basins plugins that I'll just briefly mention, will not be demonstrating them, will take advantage of the data that's built into the basin's data management system as well. All right, I'm going to talk a good bit about this tool called the Water Resources Database. And the reason why I'm going to talk about it is a great tool for processing water quality data and getting it ready for models. The Water Resources Database was originally developed in 1994 by Chris Wilson at Wilson Engineering. It was supported by the Georgia EPD, EPA Region 4, and now the Panama Canal Authority is putting a lot of resources into it. And its primary purpose was to support water quality modeling, that manage time series data for models, because some of the models, time series data can get rather large, and there's multiple sets of time series data that needs to go into the model. And then also manage monitoring data for calibration, which is kind of critical because there's not a lot of tools out there for being able to compare model results with field data. So this tool allows us to easily do that. So what I'm going to do is I'm just going to take you through the process of using WRDB, and we're going to go through a couple of different steps. Okay, I'm going to demonstrate now how to create a project, import data, and the data that we'll import will be the USGS flow data that we downloaded in basins, and then the STORET USGS water quality data that we downloaded from the water quality portal and processed with the spreadsheet. I'll show you how you get the different functions that WRDB has to summarize your data so that you can just take inventory what's there. We'll look at our STORET USGS data in a geospatial component in the GIS. We'll do some simple flow analysis. I'll show you how you could easily do data conversions, and then lastly how to export data to other file formats so that you can get it ready to go into a water quality model. Okay, our first step is we're going to create a project that we can import our data that we downloaded. Here's WRDB. I failed to mention this is a free open source database management system. It includes a good set of documentation that will help you through all of the major functions of what WRDB can do. So the first thing we're going to do is we're going to go ahead and we're just going to create a new project. So I'm going to say create, and I'm just going to call this webinar. And then I could just give it a description of what this is, so that when I go back and look, it has that information. Then I get to pick the type of structure I want to use. For a lot of us, we're very familiar with Access, and you can actually have WRDB create an Access structured file that you could also open in Microsoft Access as well inside WRDB. For my case here, I'm just going to use SQLite, and then I'm going to find a place to store this, and I'm going to actually store it in, this is typically how I do it. This is my project folder, and then I have a WRDB directory, and I'm just going to call my file webinar. You can call whatever you want to, but this is just its name on disk. And then I'm going to say OK, and then it's just going to create a bunch of blank files for us, populate some tables, and then we get to the point where we have created our project. You can see our project is described up above. So our next steps is we're going to go ahead and import some data. Okay, the first set of data that we're going to import is going to be the USGS flow data. I create separate tables within my WRDB project for each one of my data types. So I'm going to create a working table for my USGS flows. So I clicked on work. I'm going to say create new, and I'm just going to call this table USGS flows. My source was basins download. Again, being able to keep track of where our data came from. I'm going to say OK, and I'm going to close this, and then the first thing I'm going to do now is just import the data. So I'm going to go edit, import data. And I just want to show you this. These are the file formats that can be imported by WRDB from a set of different database files: Paradox, DBase, and Access, SQLite. It imports some Excel files, tab delimited, comma delimited. It's going to open up this RDB file, which is what we downloaded from Basins. Binary model data outputs, which are model outputs that are done by EFDC and WASP. WDM files, HSPF, binary output binary files, and then LSPC, so on and so forth. So these are the different types. So we're going to go ahead and we're going to pick our first gauge that we downloaded in Basins. We're going to say open, and just a couple of things. This is our data down here. This was the header that was in the file, and we just want to map them to the structure of WRDB. So the agency is going to go into agency. The site number is the USGS gauge number. This is date time. This is actually the measurement. This one here, the A, is actually a remark code in the database because this is daily average flow. So I'm going to cast that to what's called an R code. And then I'm going to have to give this a P code. So I'm going to create a new one because I don't have one there. And I'm going to call this one flow CFS because this is flow in cubic feet per second. I'm going to click OK and continue. And it's importing that data as we speak. Click continue. So now now our data is in this table. We can go and get the other ones just by doing the same thing. So we got the same mappings, and that one's brought in, and then the last one we'll bring in is the third file. And I'm just clicking this load last because it remembers the last thing it did, and that gives us all three gauges in WRDB. There are a couple of tables besides these that we should just look at real quickly. If we click up on the support table tab, which is the S, you will see that the USGS station information was pulled in from the RDB file. So there's the station ID, the station name, the station type, the lat, the long, the HUC that it's in, and that's pretty much the information. The other one is the parameter codes, and this is the one that I entered, so I'm just going to give this flow. I'm going to give it the units, and that's good enough. So that gets us our flow data into the system. Now, there are a couple things that we can do, but if we just want to do a quick summary of what's the data here, we could just ask for a report. And in this case, I'm going to ask for a report of stations and parameter codes. So here you can see our three stations. We could see that the one station had 28,000 records from 1942 through 2019, up to the date that we pulled them. The next one's just 2,900 records from 2010 to 2019. And then the last one is 38,000 records from 1903 to 2019. So that just gives us a quick look at the data that's in there. We're going to look at some other ways that we can look at the data in just a little bit. The next set of data we're going to pull in is actually the data we downloaded from the water quality portal and then processed with that spreadsheet. So I'm going to put that into a separate working table. So I'm going to close this, and I'm going to go to working, and I'm going to say create new, and I'm just going to I'm going to call it WQ data, and the source was the water quality data portal. Click OK. And then we're going to be we'll close this out, and then our next step will be we'll import the data. All right, so we're going to import. I'm going to do the edit import. I'm going to import data, and now I'm going to go over to where the portal data was processed, and now you'll see that we have a couple of CSV files. The first one I'm going to process is the WRDB station CSV that we created. And you'll see that it maps in everything across here because it automatically knows what everything is. So all of this information is actually going to go into the to the stations table. And if you remember, we had some 43 stations. So they have been 464 stations. I'm corrected there. And that data is now in the support table. These are all of the water quality stations that we processed with the portal. The next thing we're going to do is, and it's kind of important to do this in the right order, is we're going to get the parameter codes. So we're going to do an edit import, and then we'll get the P code. And again, because we use the portal spreadsheet, it knows how to map everything into the system, so we'll hit continue. And now we have in our support table, we have all of the water quality parameters that we decided we wanted to get out of Storette so that we can look at it. And then the last thing is we're going to pull in the water quality data itself, which is going to be both the Storette and the USGS. So we'll import data. So the first one we'll get is Storette, and we'll go ahead and import it. And it's pulling that data in. You'll notice that it's running into some R codes that are being added to the table. So now we have imported, let's see here, it's counting up at the bottom, about 80,000 records. So that's Storette. The next one we'll pull in will be the USGS. And again, it's going to do the same process, and then it's going to pull that data in. So it's reading the information in, processing it, and getting ready to put it into this working table. And then once it's in this working table, we can do a series of reports on it. We can summarize the parameters we have, how much data we have, so on and so forth, which I'm going to show you just in a little bit. Because WRDB is a database, you can query the data or subset the data by giving it a set of instructions. So in our case here, we have all of the Storette and USGS data, but say we wanted to know how much dissolved oxygen data we have. We could run a simple query on this system, and we can pick out of any one of the parameter codes that we have the parameter we want to look at. So let's just look at DO, and I'm going to have it query. So there's 16,948 DO observations here. I can ask for a quick summary of this. This is going to be a report station by parameters. So this will be every station that we have DO data. And it gives you a quick summary of the data, the number of observations, the mean, the min, the max, and then the time frame of the data. You can actually copy this table and paste it into a spreadsheet. You can save it, so on and so forth. So that's one way to look at it. If you wanted to look at how you have it over a spatial component by stations, there are other ways to look at it. Under reports, we can summarize by data availability, and this just gives us, I know this will be a little tough to see, but it gives us the periods of time and the stations that have the broadest range of data. So anywhere you see the green here, there's data associated with that for each one of the years. So it's a great way to just get a snapshot of the data. Or if you wanted to graph the data, time series data, you can just load this graph function, and you can pick whichever stations you want. So I'll just pick a couple here. And there's our time series data for that data. A real neat function here, there's a whole lot of functions that this WRDB graph does, but one of the neat things it does is if you find your data that you want, you can actually right mouse click and send to Excel, and it'll actually send the data into Excel so that you can look at it or pass it on to a model or share with somebody easily. And it actually creates the same graph, and then there's the data that was associated with that with that query. So some really neat stuff you can do there. The other thing is the graphing utility actually supports a series of different types of plots. It can do longitudinal plots, it can do depth profile plots, width profile, scatter plots where you can plot one variable against another, a frequency histogram, a probability plot, and a load duration curve. So if I ask you to do a probability plot, I can switch it into this mode, and now I'll just select my first station, and I would get a probability plot of the observed data. So we can see that for more than 10% or 90% of the data is above 8 milligrams per liter for our given parameter. So there's a lot of different functions that the graphing program can do. The graphing program also can graph observed data versus model output data, which there's not enough time in this webinar to cover that, but I do have a tutorial on that available on the WASP website. Alright, the next step I'm going to show you is how you can manipulate data in WRDB. So I'm going to close the graphing program, and I'm going to go back over to the flow data. I'm going to just go to my working tables, and I'm going to open up the flow data. Now this flow is in cubic feet per second. A lot of the models want this in a metric flow. So what we're going to do is we're going to convert this from cubic feet per second to cubic meters per second. And all I'm going to do is I'm going to tell the tool I want to use all of the data. So I'm going to use all of the data in this, so there is no query. And then I'm going to go to Edit, Calculate. I'm going to calculate new data. I should point out in here that the WRDB can not only calculate new data, but it can aggregate data over specific time frames, calculate DO saturation, calculates load, calculates a trophic state index, a water quality index, and annual low flow series, which I'm going to demonstrate in just a little bit. So we're just going to go new data, and then it actually remembered my my form. So I'm basically going to say I'm going to calculate it based upon one P code, and the P code is flow CFS, and then I'm going to enter the conversion factor, which I've already done here. The pound sign replaces the numeric value in the table, and it multiplies it by the conversion factor. I'm going to need to give this a new P code, otherwise we won't know what it is. So I'm going to create a new P code, and I'm going to call it flow CMS. Click OK. Oh, it must already be in my table, flow CMS. And then I'm going to create a new working table for this, because I'm just going to call it flow CMS, because that's ultimately what I'm going to be taking forward from my model. And the source was calculated from basins flow download. Again, keeping track of where my stuff has come from and going to. And then I'm going to say calculate. Oh, sorry, I just need to tell it that this is a calc. So it's going to pull the data out of the USGS flow data, and it's going to make the calculation, and then it's going to put it into the flow CMS table. And once that's done, we would have our flow data that we would need to take forward to the model. So it just calculated 70,000 records. So here is our flow CMS, and again, it looks just like this. In any one of these tables, you can do any one of the functions that I've showed you. So the next step is we're just going to do a flow analysis on this table. Okay, I'm going to show you how to do a flow analysis for the data that we downloaded with basins. So the first thing we need to do is you can only do the flow analysis on a single station. So I'm going to query out a station, and I'm going to select from my support table this station right here. I'm going to click OK, execute. So that's just subsetted that working table for just that station, which we're going to bring forward. 38,823 records. I'm going to go on to Edit, Calculate, Annual Low Flow Series. So we can see we're going to use the flow CMS. The C code was the cal, which is basically the calculated values. This is the time frame. We're going to do a 7Q10, so that's 7 for an annual, and we're going to do the minima. We're going to fill with average of values before and after for anything that's missing. We're going to output this to a new working table, and I'll just create a new table called flow analysis. Click OK, and I could put in metadata here. I'm just going to skip that for now. So that takes us into go ahead and do the analysis. I'm going to hit next. It's going to say, hey, the last available record is in April. Do you want to include this year in the annual? And I'm going to say no. And then it's telling me what it had to do for missing records. And then it's going to pair up the data, do the moving average, and then I'm going to say finish. And it's going to go ahead and calculate the series. It's going to put the information into our flow analysis table, and then ultimately it's going to create a set of plots that we're going to use for seeing what the 7Q10 was calculated at. Once it finished the calculation, WRDB actually created a plot for us, a probability plot using the Pearson method. And it shows here that our 7Q10 for this station is 16.16 cubic meters per second. And this is consistent with the same calculation that's done like the methods of D-flow. The next function I want to show you is I'm going to go back to the water quality data so that we can look at it both in a spatial component. So I'm going to go to my working table and I'm going to grab the water quality data, and I'm going to go ahead and just select a couple of parameters because I don't want to send all of this thing over to that. So I will take all of the stations, but I will take chlorophyll, dissolved oxygen, TN, TP. So we're going to just extract that out of this working table. And then what we're going to do is we're actually going to take it over into the WRDB GIS component. There's a little over 30,000 observations. I'm going to click on here, and we're going to come over to this GIS tool, which is going to actually show us the data. Let me just go ahead and add a base map so we can just see where we're at. We'll go with something simple, Google Map. It's going to go out to the web and it's going to download that map. So this just gives you an idea where we're at. So right now we're looking at where we have chlorophyll data because we've selected chlorophyll for the period of record. And actually, if we hover over these things, it's going to give you the summary on the side that shows you who collected it, the number of data points, the min, max, and the average. And actually, if we use the select tool, we can come over here and select that dot and then say show me the data, and you'll get the plot of the data that was collected there. So this is a great way to find where you have data. You also can change it from mean to the count. And the bigger the dot, the more data you have. So clearly down here we have a lot of data, so we can go ahead and do a select here just to see. And again, I grabbed 2 stations, but that's fine. It'll plot both of them. And it'll plot up the data so that you can see the data and what it looks like. So this GIS tool is very, very powerful. You can actually overlay it with model data as well, but it's a great way to do a survey of where you have data and how you could use it. The last thing I'm going to show you is how you can get data out of this system and into different file formats. So I'm going to go back to here. And remember that right now I just have chlorophyll, TN, and TP data queried. But if you go to Output, Export, you can go to a data file and you'll see that it can export tab delimited. It'll create Excel spreadsheet files. It'll create a BMD file. It'll create a WDM file. So you can actually use this to put information, to give information to HSPF. and it can create an R data frame if you wanted to take this data into R to do some statistical analysis or some other plotting routines. So it's very, very powerful what it can do. I just touched the surface of it. I can tell you from experience, anybody that starts to use WRDB and gains any kind of proficiency in it, it is going to help you organize your data better and make it easy to transmit information to other people. It'll keep your modeling project organized for sure. All right, I just want to briefly mention the model plugins that come with basins, and these plugins are developed in such a way that they actually access all of the data that is downloaded and helps put it into a form that can be used by the models. None of these are a complete package for setting up and running the models. It's just data processing to go towards the models. The plugins that are available are for HSPF, WASP, and SWIM. These are currently supported by EPA. In other words, there's somebody behind the scenes that's trying to maintain these and keep them current with the models. The SWAT, the Generalized Watershed Loading Function Model, and PLOAD are all in the form that they were several years ago, but are available for use because they still can process the data that's there. So I'll just show you how you access these things inside basins. Alright, just a little bit about the model plugins that plug into basins, and these plugins are meant to use the data that you download using the data download tool, plus any other data that you can supplement in. The plugins are located under the plugin menu, and you can see the ones that are in here. We have the EPA SWIM, EPA WASP, GWolf, the PLOAD model, and the SWAT tool. And you already saw one of the plugins earlier when we did the land use classification using the watershed characterization system. That's just a plug-in to the system. Now these plugins aren't distributed with basins directly. You need to download them again from the same site that you get basins and install them because some of these are fully maintained by EPA and some are not. Another one that's not here that I should mention because it's part of HSPF is the WinHSPF component that has a plug-in to basins for processing data. And you would just access any one of these and they would make use of the data that was there. I don't want to give any demonstrations in any of this stuff, but just a quick summary of what they can do. The SWIM model builder just does the initial setup for basins using the coverages, the DEM, the land use coverages, and then calculates the flow paths. The WASP builder tool will access the NHD Plus, and you can build a WASP stream network anywhere we have NHD Plus for virtually any size. GWolf does all the pre-processing of the land use and meteorological data to use its model. PLOAD just puts basic information into the PLOAD calculator, and then the SWAT tool again does the same thing, processes land use, soil types, meteorological data, flow paths, and does delineation. So these plugins can do a lot for you with the data that's been downloaded. Before we take questions, I need to thank my water quality modeling teammates at EPA Region 4. All of them have contributed to this webinar, have developed some of the tools that are being displayed here. Glenn Fernandez, who is a hydrologist, was instrumental in leading the effort to get the current version of basins released, working with the ORD in Athens, Georgia. Amanda Howe does a lot of work using LSPC and WASP in the region and has done a lot of work in developing tools to develop meteorological input files, filling data. John Davis works with LSPC and WASP and does a lot of work in data conversion, processing data, working with point source data, filling point source data, and is actually the one that developed the R tool that I showed here. And I will make links available to the different tools once this webinar is published on the EPA YouTube page. There'll be links there. Or if you just want to send me an email, I will send you where you can get it. With that, let's go ahead and take some questions.
Okay, thank you, Tim. We're running a little short on time, and there's a few ending items to go over here. So I don't see a whole lot of new questions. So maybe while I'm just going through some of the ending materials here, we could maybe have time for a question or two if people want to get those typed in. So just one note, there will be an evaluation screen that pops up at the end of the webinar today. We encourage you to answer the evaluation. It gives us feedback on these webinars that we do, and we do listen, do read all of the feedback and try to improve our webinars whenever we can. As I mentioned earlier, if you have any questions for Tim, as he just posted on the screen, please feel free to get in contact with Tim. He has a great team there in Region 4 that are they're all very proficient at a number of different water quality models. And I think Tim is going to briefly talk about a modeling workshop that's coming up that's free. Tim, do you want to say a few words about that?
Yeah, so registration is now open for our water quality modeling workshop. It covers general principles about water quality modeling. The model we use is WASP. We actually do hands-on application of the model in a real-world situation. The instructors are myself, Bob Ambrose, James Martin, and Chris Knights. Bob and James and I have been the ones that are instrumental in developing the WASP model. So feel free to sign up. It's free to the public. The only thing we ask you to do is you have to bring your own computer to work on.
Great, and there's a website at the bottom of the screen there that you can get more information on the workshop and the WASP tool, or you could just Google that and that would come up, or email Tim. I think we have a couple more quick slides. You can download a certificate of attendance today at the link shown on the bottom right-hand corner of your screen. I think that's maybe popping up now. And you can just click download files to download the PDF. More importantly, you can find information on future webinars as well as a recording of today's presentation on EPA's Water Quality Modeling Workgroup website. And the link to that website is shown on the screen right now, along with my name and contact information and Tim's. And I guess lastly, we do intend to continue this webinar series. We've got some good topics coming up. I believe, Tim, we were even discussing a basins-only webinar, right?
We could. We're thinking actually of doing one with LSPC and demonstrating the LSPC plugin that will build a complete LSPC setup. Okay. Well, anyways, yes. With that, I think we're going to end today's webinar. Just a big thank you and round of applause to Tim and his team. Thanks. That's a very complex webinar. We appreciate all of the kind of action demos there that you did. I think those are really helpful. And oh yeah, our next webinar is already set. It's going to be on the EPA model Aquatox. The date, it was just flashed up there real quick. The date for that will be announced soon through kind of our normal distribution channels and on our website. And with that, thank you everyone, and we're going to end the webinar now.